Kirchhoff's voltage law tells us that the sum of the voltage rises minus the voltage drops around a closed loop has to equal 0. And that's what we're going to explore in this video. So in the first example, sometimes it's easier to see this with numbers. I've already given you the circuit and the current and the voltage drops here. So what we're going to do is we're going to start at ground. I like to start at ground when I create these equations. And starting at ground, the first thing we encounter going in this clockwise direction is a 10-volt source, and we know that it is a voltage rise because it's going from minus to plus. That means we're adding 10 volts at this point. So that's going to be a voltage rise. So I'm going to add the voltage rises, and I'm going to subtract any voltage drops as I counter them. Okay, as we continue on around this path of current in the circuit, we see that this resistor here is going to cause a voltage drop. Remember, a voltage drop is the energy required to push that current through that resistance. And so that is going to be a drop of 4 volts. So I'm going to subtract that. And again, we know it's a drop because we're going to have more voltage on the entering side than we do on the leaving side. So we're dropping 4 volts at that point. We're going to continue after that resistor to another resistor, and we see that it's going to require 6 volts to get past that resistor. Again, that's just the energy required to push that current through that resistance. And when we get to the other side, we see that we're back at ground, and that is our closed loop for this particular circuit. And then once we get back to where we started, we know that that has to equal 0. So that's where I'm going to put in the equal 0 when we get back to where we started. And as you can see, 10 minus 4 leaves 6, minus 6 leaves 0. So that works. And that's a pretty simple example. I wanted to show a slightly more complex example next. And that is right here. So in this circuit, we can actually use a few different loops. I'm going to show you a couple different ones that we can use. And the loop doesn't always take a path of current in this, or at least not the same current. So we will kind of talk about that as well. But the first loop I'm going to look at is the one right here. I'm going to start in this loop, and we're just going to follow this path. So I'm going to start at ground and go in this clockwise direction. And we encounter a voltage source, and we see that the orientation shows it's going from minus to plus, meaning we're adding 10 volts here. So for my first equation, I'm going to call this KVL 1. I'm going to add 10. Let's continue after the voltage source. We get to a resistor, and we see that we're going to lose voltage across that resistor. This is based on the direction of the current. If you're not clear on how that voltage drop is found, you might want to look at some other videos. So we see that there's a drop of 5 volts here, so I'm going to subtract 5. And we're going to continue around. Now at this point, I'm just going to look right here and go down this direction. That's going to be the loop that I'm looking at. And I see that I come to another 10 ohm resistor, and that is also going to be a drop of 5 volts, as you can see, because again, that's the direction of current. And then when I come back from there to close my loop, I get back to ground, so I'm going to say that equals 0. 10 minus 5 does indeed equal 0. Now let's say instead of this loop, oh, I didn't mean to lose that. Instead of this loop, maybe I'll switch to a different color here. Instead of this loop, I'm going to use let's do this loop. Let's go around the outside, the whole circuit here. So I'm going to, again, start at ground, and I encounter this 10 volt source, which again is a voltage rise. Not all sources are going to be a rise. It depends on the direction of the source. But in this case, it's a rise in that clockwise direction. Now continuing on, again, I encounter this 5 ohm resistor, which shows me that I have a 5 volt drop. I'm going to continue on this way, and I encounter a 5 ohm resistor. This one has a 2.5 volt drop, so I'm going to subtract 2.5. Continuing on, I subtract another 2.5. The difference, the reason these have a different voltage drop from the other 5 ohm resistor is because the current's different there. And again, that's something for another video if you need to find that. And then when I get back to this, this path here, I'm back at ground. And so I'm going to set the whole thing equal to 0. So 10 minus 5 is 5, minus 2.5 is 2.5, minus 2.5 is 0. So again, that checks out. Let's try one more. Let's look at this loop right here. And I'm going to change colors again just because I want to show you what we're doing here. So let's start again at ground. Ground is down here. And this time I'm going up through this 10 ohm resistor. Now notice that when I come up through this 10 ohm resistor in this direction, I have a minus to a plus. That is a rise. Even though we're talking about voltage across a resistor, that's a voltage rise. So I'm going to say my KVL 3 is 5 volts, a plus 5. And then continuing on, this is going to be a minus 2.5. And then continuing on, that's going to be another minus 2.5. And then continuing on, I get back to where I started, which has to equal 0. So 5 minus 2.5 is 2.5, minus 2.5 is 0. Okay, so there's 3 different KVL equations for that circuit. Now, one of the strengths of KVL is that we can use it to figure out voltages that are unknown to us. Now, this is a transistor circuit, and you don't really need to know about that. We're just going to apply our KVL, just like we did in the earlier circuits. So let's say what we really want to know is what this Vx is right here. That's an unknown voltage. Now, we do know that we have 5 volts here. We know there's a voltage drop across our transistor from the base to the emitter. Again, it's not important that you know that or what that is. And we also know that there is a 1.5 volt drop here. And I noticed that for this path here, the only unknown is that Vx. So if I write an equation knowing that the voltage rises minus the voltage drops has to equal 0, I can find Vx. So let's write our equation. Again, I'm going to start here at ground, and I encounter the 5 volts here. That's going to be plus 5. Continuing on around this loop, I encounter a voltage drop. I don't know what it is. It's just Vx. So I'm going to subtract Vx. And then when I get here, I see that there's a 0.7 volt drop there. Continuing on, I see that there's a 1.5 volt drop across the resistor here. And then continuing on, I am back at ground. When you see grounds, they're connected to each other in your circuit. So when I get back to where I started, I have to set that equal to 0. So if I move the minus Vx to the other side, it becomes a positive Vx. So I have 5 minus 0.7 minus 1.5 equals Vx. So that would be 3.5, 2.8 volts is Vx. And it would have to be because Kirchhoff's voltage law has to be upheld there. See if you can, you might want to pause the video and see if you can figure out Vy using the same rationale. And I'm going to explain it right now. We're going to write our own equation here. And this time I'm going to use this side of my circuit. Now, this may be a different way for you to see this, but I'm just going to draw this as if we have a 15-volt source over here. Okay, because that's what we have up here at our VCC. And let me draw this equation for you. So this KVL equation went with this KVL loop. And then my second KVL equation, I'm going to start here going up, and that's going to be a voltage rise of 1.5 volts. I'm going to have some Vy that is also a voltage rise. Again, in this clockwise direction, it's going from minus to plus. So that means, of course, a voltage rise. My 7.5 volts, which is a drop in that from the top to the bottom across the 2.5 kilo ohm resistor, but I'm going in that clockwise direction. So that's why I'm going to add it. And then when I get to the 15-volt source over here, I'm actually going to subtract it because in that clockwise direction, we're going from plus to minus. So we're it's a drop in this case. So that's what I meant when I said a source might be a drop, depending on the direction that you're looking at. And then when I get back to ground, of course, I've got a ground here and a ground here. I set the whole thing equal to 0. And then I can solve for Vy, which should be 6 volts. I hope that was helpful with your Kirchhoff's voltage law, and please follow for more videos.